Hi. In this video, we will use again the timer counter, but this time we will use the interrupt that can be generated when this timer overflows. We will also introduce another environment, which is the STM32CubeMX tool, which can be used to prepare our code and minimize the new code segments needed to do our project, to make our project. What we plan to do is that we will set up the timer with an appropriate period, and when it overflows, it will cause an interrupt, and within the interrupt service, the LEDs will be toggled. So we will get the same result as we had in our previous exercises, in the previous videos, but this time we won't toggle the status of the LEDs within the main with an infinite loop and with an artificial delay caused either by a dummy loop or by continuously checking whether an overflow has occurred. Instead, in our infinite loop in the main routine, we will do nothing. But when an interrupt occurs, within the interrupt service is where we are going to toggle our LED status. So, first of all, let's start the STM32CubeMX tool that will be used here. It's a relatively heavy tool, so it takes a while to start. Okay, there are plenty of projects I already created, but we will create a new project here. The system is initialized. Be careful when you install the STM32CubeMX tool, but also during its use, it's better to have an internet connection because many things may need to be downloaded in the development time of a new project. You can see now in this screen the list of the processors and the tools. So we will find our own. It's STM32F407. 407 VG. Here it is. Yes, this one is the type of the microcontroller used in our STM32 discovery board. So I selected the correct microcontroller. I start the project. And now, in this first screen, I see the pin layout of the microcontroller. And since we said that we were going to use the LEDs, the 4 LEDs used in the previous exercises, we first have to make the pins that are connected in the specific board to these LEDs to set them as outputs. This is the PD12. So by a simple click, I have this list here and I choose GPIO output, and I do the same for the other 3 pins where the 4 LEDs are connected in the specific board. Okay, and I also, from the list of the peripherals at the left, have to select the timer and do some configuration. Let me see my notes to make sure that I won't forget some crucial settings. We've already done this. So now we go to the timers and select Team 2. Okay, here is what I have to do. So I select Team 2. And first of all, I will select as a clock source for this timer the internal clock. I get some configuration parameters below. You can see some very useful things that we have already seen them directly in the code in the previous video where we did not use the STM32CubeMX. And these parameters are, for example, the use of prescaler if we like to use such a prescaler. The counter mode if we like to have a counter, an up counter or a down counter. And the clock, the counter period, where we could select which is the top value that can be used. Let's leave the default values here for the present, but since we like to use an interrupt that will be triggered when the timer overflows, we have to have in mind that the ARM Cortex core within the STM32F407 microcontroller is a generic ARM core that is built using a set of interrupts, a large number of interrupt sources. I think it's about 240 interrupt sources, but the developers of the ARM core do not have any idea which kind of source for each one of these interrupts will have during the implementation on a specific microcontroller. So we do not have only to set up at the peripheral level the interrupts at the level of the Team 2 timer counter, the interrupts, enable the specific sources we like, but we also have to enable the corresponding interrupt at the ARM level, at the ARM core level instead of the peripherals level. The ARM core handles all these interrupts using the nested vector interrupt controller, and its settings are here. So concerning Team 2, we have also to set the Team 2 global interrupt enable at the NVIC level, which is the ARM core level, the ARM Cortex core level. Okay, we selected internal clock, we selected Team 2 global interrupt. Let me see in my notes if there's anything else we should choose. Okay, we did not change any of the default values that we set earlier, so we can move directly to the next stage, which shows the clock configuration. One can get advice from this block diagram in order to understand which are the clock sources and how do they reach specific peripherals. We won't analyze this now. The project manager simply within the project manager, we will simply set the name of our project. Let me call it, although I have already used this name in my test, Team 2 Interrupt CubeMX. Okay, let's use the same name, Team 2, Team, change to English, Team 2. Interrupt cube mx and I will select the project location, but I would not like to mix with the already existing this one here, so I will go within the new lab and add this file here, this whole project directory. And the last thing very important that we have to select here is that we should select the correct toolchain IDE environment. And this is the MDK ARM. what this will do is that it will create a skeleton, a template project that can be readily used within the Kale microvision environment that we have already used in our previous videos. So it's important to select MDK ARM here. And there's nothing else I think that we should do. We simply click on the generate code in order to generate an appropriate project. This is the reason I told you earlier that we should have an online internet connection, because some things may need to be connected. So I press yes for any necessary downloads that have to be made. And wait for a while. Okay. We paused for a while video recording in order to complete the downloading. And now downloading has been completed and code has been generated. So let's open the folder. It shows that there is a problem here, but let's check it more carefully. Let me go to this directory and see what was generated. Working. Here is where it should have been created. This is its directory. And here is the MDK ARM. So if I click this icon here, I guess that the project that has been generated will open. Let's close the STM32CubeMX and keep only the microvision. Okay. Let's see if it has been indeed created correctly or with some problems. Let's see the next steps. First of all, if we visit, for example, the main routine, you will see that STM32CubeMX created some skeleton file with some comments that direct us where to add our code. There are plenty of things here, some initialization routines that are declared, and within the main, some initializations, but they're not complete. For example, it is called MX GPIO init and MX Team2 init, which are routines that initialize or we expect to from them to initialize these peripherals that are going to be used. And there is an infinite while that does not do anything here. If we go below, we'll see the initialization routines mentioned earlier. For example, we can see here the MX Team2 initializer. All these initializations correspond to what I showed you in the window of the CubeMX earlier. But let's move a little bit and see what problems will we have. Let's first of all try to compile the project as is without adding anything else. Project, build target. Let me see my notes for a while. If we get an error such as this, no section matches selector, we will have to do some additional things, but let's see if we will get this error. Yes, we get this error. So let's see from my notes, what do we have to do? We have to open the Manage Runtime environment and go to the devices to click the startup option that we did in our previous projects. In the device, you can see that this time startup was not created automatically. However, as you will see, there will be created some additional files twice, and we have to remove one of them. So initially, let's check the startup. Let's move to see more clearly. Here, we got these new files here that have been added. But there are some of them have already been declared twice. So let's see which one has been already declared. Here it is. Under driver CMS IS, we have the STM32F4XX, and we have also created it here. So we have to remove it, I think, from this point. Let me see again my notes. Yes, so we remove it from driver CMS IS. Delete, remove file, okay. And let's try to build now the project. Again. Good. So we get 0 errors right now. Although there are plenty of things that have to be done, we will connect the board and start debugging it without any new code added, to see what is wrong and what has to be inserted concerning the code. So let me connect, first of all, the board. Open the options here. We see that things concerning the C++ compiler have already been added from the CubeMX tool, but I have to go to the debug and change to the ST debugger in order to connect with this method to my board. No JTAG, but software. Okay, it is found, as we can see here. So it is okay, I think, and we can download this project. Okay, now we can start running the project. We will see that nothing happens, and we will stop the debugger to see where it has the problem has stalled. So if I start a debug session, and I start running, you do not see it, but nothing happens on my board. But if I stop running to see where it is, we will see that it has been stuck within the infinite while loop. What we would like to see what happens concerning the timer counter TIM2, because we have to see, is this counter measuring? Is this counter causing anything concerning the overflow, an interrupt, for example? So we will add a new window, as you will see from my notes. We will find we can make it appear from the peripherals menu, system viewer. Let's see it, peripherals menu, system viewer, TIM2. Here it is. So if you read the manual, you will see that all of these names are the peripheral TIM2 names, the control register 1 and 2. These have some specific bit fields. where you can find their meanings from the datasheet. I won't spend any time here trying to explain all these things here. But there are also some registers already seen in our previous project, in our previous video. For example, ARR, which is the top value that can be read, that can be reached by the timer, the status register, which shows if an overflow has occurred, and other things like this. Okay. And there's also the CNT. This is the most important count register, which shows actually the value of the counter. So if we continue running, we would expect, even within this infinite loop, we would expect something to change at the current value of the timer, but that does not change, which means that the counter is off. It does not count. What should we do next in order to start this? So, first of all, we have to find out where is the error handler. We will find our error handler within. I stop debugging in order to see all my files more easily. There is this file here, which has all the interrupt handlers. One of them is the one we need for our, here it is, for our interrupts, for the interrupts caused by the TIM2 IRQ handler. So we would expect that we would reach this point somehow here. So I start debugging and I place also a breakpoint. But the problem is that we not only do not reach the IRQ handler, we have a counter timer that does not count at all. So there's something more fundamental that we should do. And this is to call an initialization routine that starts the counter. So this initialization routine is this one here that has to be placed within mx-team2 init. This is within the main file that we saw at the beginning. Here is the initialization. If I go to the definition of this routine, okay, so here I have to, let's see in which point, at the end of this routine. So let's go at the end of this routine. Here it is, user code can be placed here. So I copy paste this initialization command. Okay. This will start actually the counting, but I'm not sure if it will reach the interrupt handler. Let's start debugging and see what happens. No, actually, I have to compile before I start debugging. So stop debugging and first do the compilation. Build project. Okay. And then now I start debugging. Okay. Good. So I will also visit here the interrupt routine of handler of TIM2 counter, and I will place a breakpoint here. Insert remove breakpoint in order to see if this interrupt handler will be reached somehow. Let's start debugging. Let's start running actually. This one here. Okay. It reached the interrupt handler. That's good. But let's continue. Now, I'm not sure if it will be reached again. It is running. It is currently running. But does not seem to visit this interrupt handler. So let's pause for a while our run to see what happens in the CNT register. Is it really counting? No. At least it does not seem to count, or it has count once and did not continue counting again. There are some things that we have also to add here. So let's stop debugging our code and see what else is needed here in order to fix our interrupts. Another issue, let's take things one by one. I think we have already or have not. Let me visit again this routine here. Go to the definition and see what did I... No, I enabled the interrupts, but I did not add the correct command that will enable the counter to start counting. And this command is this one here. So I have to also copy this one here. And now we have this if command that lets the counter start counting, and this command here that I added earlier that enables actually the timer. But I have also to place them both there, I think. Okay, what else? We also have to add what we would like to do within the IRQ handler. And this is the code. Let's also add this one to here and see overall the project. So I will move again to this interrupt handler. And I replace it with all this code here. As you can see, the first command gets the source of the interrupt. We ask, is it UPD? UPD is for timer overflow. So I check whether this is an overflow. In this case, I clear this interrupt source in order to stop continuously causing interrupts. And what I do is that this time I toggle the status of the LED pins. Watch out, this can be easily done using this call here from the hardware abstraction layer services. And if they are turned on, I turn them off. If they're off, I turn them on. Okay, let me see if there's anything else that we can change. Yes, we can also reduce the period of the counter because it's too long to wait for this value. So I will reduce it somehow. And there's also something else we should do is to enable these interrupts before the while loop in the main routine. So I return to the main routine. Before the while, okay, here it is. I also globally enable the interrupts at the NVIC level probably. And I will also visit the initialization again here and replace this period with a smaller one. One, two, three, four, five, six, 7 instead of 8 Fs. So I think now we can, and I believe there's nothing else we can do, and I think this time our system will run correctly. So build the project again. Okay, 0 errors. Let's start debugging. I will also place again a breakpoint. Here it is. It remains at the point where it was in my previous run. So let's see if we will go within this interrupt handling routine once or twice or whatever. So let's run. Okay, I directly reached the interrupt service routine. Let's continue running to see if it will go again. And watch out, I have the counter counting. You can see it? Here it is. So let's run again, continue running again. And it went again here. You do not see it, but you will see it in a while. But all my LEDs have been turned on now. So you can hear me and you can also see the breakpoint here. So when I press continue, the LED's status was toggled, and I wait until overflow reached. Here I am. I stopped again to the breakpoint. I press again continue. The status of the LEDs was changed, was toggled. So here I am again. I wait for overflow in order to visit the breakpoint. Here I am, stopped again at the breakpoint. Once again, overflow, breakpoint, and let's remove the breakpoint and see continuously. Okay, I removed it and see continuously the LEDs blinking. Of course, the period may be long, excessively long compared to previous examples, but it is blinking. And off.